So now we've seen that mathematically the movement of an electron is likely to show some very different kind of velocity, a group velocity, compared to just the underlying velocity of an electron wave, a phase velocity. We're going to look now in more detail at the motion of an electron. To do so, we're going to have to construct what we will call a wave packet. A wave packet is a superposition that, when we add it all up, gives us a state that corresponds to the electron being within some region of space, rather like a pulse. We're going to construct one now and explicitly see what it does as time goes forward.
So let's construct a wave packet then by putting together a linear superposition of energy eigensolutions. For a free electron or a similar particle of mass m, we know that the individual eigensolutions are plane waves. So, for propagation in the z direction, these plane waves are of the form e to the I omega t minus kz. But we have to allow the omega to be something that is a function of k. And in general, what we're saying is that this omega is E divided by h bar, but remember the energy E is some function of k. Anyway, this is one of our possible eigensolutions for some given energy E or some given wave vector magnitude k. And hence it has this energy E of k, h bar squared k squared over 2m, and that means that our frequency is, of course, just E divided by h bar. But remember that E is in general a function of k, so we can imagine ourselves as choosing k here, and that will determine also what E and therefore omega are. One convenient and useful set of k values and amplitudes to choose would be, first of all, to equally space the k values. That's going to be mathematically convenient to do. And then we could choose a specific set of weights or amplitudes ak, and what we might choose here would be what we would call a Gaussian set of amplitudes. You may recognize this function, e to the minus something squared here. You get a nice peaked function, a nice smooth peaked function out of that. It's a very convenient one to work with. It also happens to have nice mathematical properties. We don't have to choose this form of wave packet. We'll get the same kinds of phenomena with other similar kinds of pulses, but this one is mathematically rather nice. So these are our AKs in here, and here are our different plane waves, and we're going to choose the Ks to be equally spaced. And there's a width parameter on this Gaussian that we put in, this delta K. This K bar here is the center of the distribution of K values. So if we have a Gaussian function like this, the K bar is the value of K in the middle of that. And as I said, delta K is a width parameter for the Gaussian function. One of the really good reasons to use a Gaussian is that this Gaussian, which we're setting up in K, also gives us a pulse that is Gaussian in space. So it gives us not only a pulse that is a nice Gaussian shape when we're looking at the different K amplitudes for the different waves here, it also gives us a pulse that is a nice peaked pulse in space. So let's look at a Gaussian wave packet then. As I said, our Gaussian wave packet is also Gaussian in space. And here is just such a wave packet. So we haven't started it moving yet, but here's our wave packet. This is the result for the probability density in space of us having chosen that Gaussian set of weights for equally spaced K values. Now we're going to let time evolve. We're going to let time move forward. And remember, inside our wave packet, each of those components, each of those particular plane waves, has its own oscillation frequency built in. And we're just going to let time move forward and let all of these oscillating waves add up. And let's see what happens. So we're going to let time evolve. As I said, simply adding up the terms in our wave packet sum at each time, we can see the wave packet propagate. So let's watch it do that. So what we've just seen is that the wave packet moved to the right and it got wider as it went. But it certainly moved, so there was kind of a velocity of the center of this peak. And I can tell you that the center of that peak is indeed moving at the group velocity. Let's look at it again here. Now look at the fact not only that it's moving, but also that it's getting wider. A wave packet that increases in width as it's propagating is said to be dispersing. It gets wider in this case because the change in omega with k is not even linear. It's not at all linear. It's quadratic. And that effect of the consequence of omega not being linearly proportional to k in any way that we look at it gives rise to what is called group velocity dispersion. So look again at this pulse getting wider as it goes out. It is propagating forward at the group velocity, but it's also getting wider, and that's because the group velocity itself is not even a constant. The group velocity itself is also a function of k. Now let's look at a more complicated situation where we can begin to see some rather interesting things happen. And the situation we're going to look at is a wave packet hitting a barrier. So suppose then we want to understand this problem, and we're going to hit a barrier from the left, and here's our potential barrier that we're going to hit. We can proceed in the same kind of way as we've just done before. But now we're going to use a superposition of the energy eigenfunctions of the Schrödinger equation in the presence of this barrier potential. Now this is a kind of problem we can solve. We'll talk about roughly what the solutions would be like. We're not going to go through the algebra here, but we can solve this problem. For any particular energy we come in with here, we can actually write down the solution to this problem. So here's our barrier potential, V of z. So if we want to solve that problem with our energy eigensolutions in the barrier, we know what those are going to be. We can work these out if we want to. For a particle incident from the left, we're going to have forward waves and backward waves. And inside the barrier, we're going to have exponentially decaying waves and exponentially decaying waves in the other direction if our energy is below the top of the barrier height. Or if it's above the top of the barrier height, they will actually be propagating waves in both directions. And then on the far side, we will have a propagating wave again. So as I said, this is a problem we could actually solve. Algebraically, it's not too hard, and we could write this down. For any specific energy we chose here, we could write down the form of the energy eigenfunctions of this problem. So let's look at what happens when we do that. We're going to construct, just as we did before, in our computer, a Gaussian weighted linear superposition of solutions. But now these solutions are these ones that have got forward and backward waves here, forward and backward exponential decaying waves in here, or possibly forward and backward propagating waves in here, and then a propagating wave going out on the right. So we solve all of these for different k values, and we construct a Gaussian weighted superposition just as we did before. Again, we would use equally spaced k values on the left and have them centered around the k value here corresponding to that orange dashed line. And we see that, as before, it gives us an approximately Gaussian-like pulse width on the left here. Now we let the time evolve. We simply multiply the omega t factors inside our complex exponentials and see what happens. And what's going to happen is the pulse is going to move to the right. It's going to partially bounce off this barrier and partially transmit through it. Note, incidentally, that there's a significant probability of finding the particle inside the barrier when the pulse is hitting it. If we move up to a higher average incident energy, then we'll get similar behavior, but now the transmitted pulse will be stronger and the reflected pulse will be weaker. Incidentally, in these distributions I'm using here, there's quite a large sum of different energies of solution, some of which are above the barrier and some of which are below the barrier, required to construct this wave packet. So here we see a stronger pulse going out to the right than we did before, and a somewhat weaker pulse had gone off to the left here. Here it is again. And if we come in above the top of the barrier, even in that case, there is still significant reflection of the pulse. Now that might surprise you if you took a classical view of the problem, because if I came along with a ball above the top of some wall here, the ball would just fly right over the top of the wall and it wouldn't notice the wall. But for these waves here, that's not true. When they see this discontinuity or this change in the potential, they reflect off that. Even if none of these k vectors involved here, k magnitudes, corresponded to an energy that was below the top of the barrier, even if they were all above the top of the barrier, we would still get some reflection here. So here's what happens when we do that. Waves are generally reflected of any changes in the potential. And we saw here that we got a much larger amplitude of wave going off to the right and relatively little reflected, but we still did see some reflection. There's still some reflection here.
So now we can understand how particles with mass, such as electrons, move through space. Though they are waves, and we can think of waves as moving, it turns out that the simple velocity of that wave itself, the phase velocity, is not a good guide to the real velocity of the particle. We have to use this concept of group velocity as a much better way of looking at how fast the particle is going. It is actually always the case with waves that this group velocity is the better velocity to use. With classical waves, under many circumstances, it just turns out there's not usually much difference between the phase velocity and the group velocity. That is largely because the phase velocity itself does not depend much on frequency in many cases with classical waves. That is, the frequency is often proportional to the wave vector magnitude to quite a good degree of approximation. Remember, the phase velocity is simply the ratio of the frequency over the wave vector magnitude, that is, omega over k. So saying the frequency is proportional to the wave vector magnitude is the same thing as saying that the phase velocity is a constant. In the quantum mechanical case, for example for a free electron, we saw that the relation between the frequency and the wave vector magnitude was very much not a proportional one. In fact, the frequency for a free particle is proportional to the square of the wave vector. Hence, this issue of using group velocity becomes very important in understanding the motion of quantum mechanical particles. We have seen how a wave packet, a pulse in space, can propagate through space. The group velocity, essentially the velocity of the center of the wave packet, is the velocity that makes sense compared to our classical notions. For example, we saw it reconstructs the classical relation between kinetic energy and velocity. We did see, though, that the pulse or wave packet spreads out or disperses quite noticeably as it propagates. Again, a consequence of the lack of proportionality between frequency and wave vector magnitude. We have also seen how this particle wave packet partially reflects off boundaries, again, a very non-classical phenomenon, and can tunnel through barriers with a probability of appearing on the other side. So, though this behavior was perhaps different from what we were expecting classically, we can see that we are beginning now to get some intuition in how quantum mechanical particles move, in a mixture of what we expect from waves and from particles, though all these effects are correctly explained with the wave view from Schrödinger's equation.